Okay, today we're going to look at the natural logarithmic function and its derivative. But before we start, just a brief reminder of the general power rule, which was x to the n dx. When we integrated that, we said that it was x to the n plus 1 over n plus 1 plus c, but hopefully you remember there was a stipulation that n cannot be equal to negative 1. And we'll see the reason for that when we look at the definition of the natural log. I'm going to abbreviate here, the definition of the natural log. We looked at the natural log last year, but we didn't really give it a definition, because now we'll see that the definition of the natural log, it's defined in terms of an integral. It goes from 1 to x of 1 over t dt, and x has to be greater than 0. In other words, the domain is the set of all positive real numbers. So this is the actual definition of the natural log. Here I have graphed y equals 1 over t, which is the derivative of the natural log, evidently, because if the natural log of x is the antiderivative from 1 to x of 1 over t, then 1 over t must be the derivative. So if we go ahead and graph that, if x is greater than 1, x is some value greater than 1, and we're going from 1 to whatever that x value is, remember that would represent this area to whatever we said x was. And this is going to give us a positive value. So if x is greater than 0, then the natural log of x is also going to be greater than 0. Likewise, if x is less than 0, not less, these both, if x is less than 1, this one should have been 1. If x is less than 1, that's going to be the same as the opposite of the integral from x to 1, in other words, of our 1 over t dt. We're going to be going backwards. We're going to be going, say, x is over here. If we start at 1 and go backwards, that means that the natural log of x is going to be less than 0. If we integrate from 1 to 1, if I'm going to try to figure out what this is, hopefully we remember our properties that says that if we're going from 1 to 1 or a to a, that's always going to be 0. So in this case, let me erase this. This x was 1. So we know that the natural log of 1 is always going to be 0. I want to think about some properties of the natural log of x. We learned last year that the natural log of x looks like this function. Its domain is from 0 to infinity. Its range is negative infinity to positive infinity. Notice it's going to keep increasing slowly, but it keeps increasing. This is a continuous function. It is an increasing function. And it is a one-to-one function, which means it has an inverse function. And it is concave down. So those are just some things that we can observe about the graph of y equals the natural log of x. There's some properties of natural logs that we learned last year. One of those properties, and we just talked about this, is that the natural log of 1 is 0. The natural log of a times b can be expanded to the natural log of a plus the natural log of b. We worked with that a good bit last year. Likewise, we learned that the natural log of a to the n can be rewritten as n times the natural log of a. And finally, the natural log of a over b can be expanded to the natural log of a minus the natural log of b. Now, these are some properties that we're going to be using as we begin to take derivatives of the natural logarithmic function. Now, the base of the natural log is e. And that's one of those irrational numbers. It's approximately 2.71828, and it's going to keep on going and going and going. You can always use your calculator if you are using that, but the definition of the natural log of e, the natural log of e is equal to the integral from 1 to e of 1 over t dt, and that's always going to be equal to 1. So the natural log of e is always equal to 1. So sometimes we use those properties to help us find derivatives, but let's see how we find the derivative of a natural log. And I think you'll like this better than some of the other derivatives that we've taken before. The derivative of the natural log if let's let u be a differentiable function. Let me make that a little bit better, u. Let u be a differentiable function of x. Then, first of all, simply the derivative with respect to x of the natural log of x. We should already figure out what this is from the definition of the natural log. That's simply 1 over x, where x is greater than 0. But if we have the derivative with respect to x of the natural log of u, this is going to be u prime over u, and again, u has to be positive. So let's just quickly take some derivatives. I want to take the derivative with respect to x of the natural log of 2x. Well, we said that's going to be u prime over u. Here's my u. So the derivative is going to be 2 over 2x, which is equal to 1 over x. Let's take the derivative with respect to x of the natural log of x squared plus 1. Again, u prime over u. Here's u. So the derivative is 2x over u, x squared plus 1, and we can't do anything to simplify that derivative. Okay, we know things can't always stay simple, so let's look at this derivative. Still not difficult, but we have to remember that we can still have the product rule or the quotient rule, the chain rule. So and this is a case of the product rule. So when we take the derivative, it's the first term times the derivative of the second. And just for practice, let's write it out this way this time. The first term times the derivative of the second plus the second term times the derivative of the first. So we're going to have x times, now the derivative of the natural log of x is 1 over x, plus the natural log of x. And the derivative of x is simply 1, so we get 1 plus the natural log of x. And then let's look at one that would involve the chain rule. The derivative of the natural log of x cubed. Here we have to use a chain rule, which says we take the derivative of the outer function times the derivative of the inner function. And there's not much we can do unless you want to rewrite it this way. And I would be sure to use parentheses because it's not the natural log of x squared, it's the natural log of x squared over x. And that's as much as we can do there. Now there are times that before we can take a derivative, we may have to do some simplification of our natural log. If this is our function, y equals the natural log of the square root of x squared minus 4. It would behoove us to use those properties of natural logs and rewrite this. And we can rewrite it as the natural log of x squared minus 4 to the 1/2, which is also 1/2 times the natural log of x squared minus 4. We just kind of expanded that. And now if we want to take the derivative, y prime is going to be 1/2 times derivative of u over u, and the 2's will cancel. And our derivative is x over x squared minus 4. So very easy to do once you rewrite that using the properties of the natural log. Let's look at another one that looks a little more complicated, but if we will rewrite it and expand it, we'll find that it's very easy to take that derivative. X times x squared plus 1 squared over the square root of 2x cubed minus 1. First step is to see if we can expand this. And we said multiplication we can rewrite as addition, and division we can rewrite as subtraction. So we could rewrite this as the natural log of x plus, I'm going to go ahead and put twice the natural log of x squared plus 1, moving that exponent to the front, minus, move this over just a bit, 1/2 the natural log of 2x cubed minus 1. Now this is in a form that it's going to be much easier for me to take the derivative. When we take the derivative, well, the derivative of the natural log of x is 1 over x, plus twice the derivative of u over u, which is x squared plus 1, minus 1/2. The derivative here is 6x squared over 2x cubed minus 1. And we don't want to leave it like that because that's an easy simplification. That cancels, and that cancels to a 3. So we get 1 over x plus x over x squared plus 1 minus 3x squared over 2x cubed minus 1 as our derivative. Now there may be times when we use logs to differentiate non-logarithmic functions, and usually you'll get that instruction, or you may just look at the problem and think it might be easier to do it with logs. So let's see a case where we might do this. Here is our non-logarithmic x minus 2 squared over the square root of x squared plus 1. And of course, we're going to say that x cannot be equal to 2, because that would give us a 0, and we can't have a log of 0. So if we're going to differentiate this using logarithmic functions, obviously you could do it using the quotient rule, but we're going to do it using logarithmic functions. We're going to take the natural log of both sides. We did that last year in solving equations. So if we take the natural log of one side, we have to do it to the other side. And we're just taking the natural log of x minus 2 squared over the square root of x squared plus 1. Just like we did before, we're going to expand this, and we're going to have twice the natural log of x minus 2 minus 1/2 the natural log of x squared plus 1. Now, when we take the derivative, remember we said it was u prime over u, and we're trying to solve for y prime. So when I take the derivative of the left side, we're going to have y prime over y, u prime over u, equals, now over here, when we take the derivative, we're going to get 2 over x minus 2 minus 1/2 of 2x squared, 1/2 of 2x over x squared plus 1. Well, those 2's are going to cancel, and I'll have minus x over x squared plus 1. We're getting closer, but I want y prime, not y prime over y. So we're going to multiply both sides by y. So y prime equals y times 2 over x minus 2 minus x over x squared plus 1. And we can go back and substitute. We said originally that y was x minus 2 squared over the square root of x squared plus 1. And I'm going to get a common denominator here. I know y'all will love that. Common denominator is going to be x minus 2 times x squared plus 1. We'll cross multiply here and get twice x squared plus 1, which is 2x squared plus 2, minus x times x minus 2. I'm going to combine some steps here. It's going to be minus x times x is minus x squared, minus x times negative 2 plus 2x. And I think now you'll see the reason that I did that. Notice one of these cancels here because we are multiplying. We can do that. Make myself some room. And we have now x minus 2 over x squared plus 1 to the 1/2 times x squared plus 1 is x squared plus 1 to the 3/2. Just add your exponents, times 2x squared minus x squared is x squared plus 2x plus 2. So this is an example, and you may have to go back and look at it again, of using logarithmic differentiation for a function that is not a log function. Now remember, well, hang on just 1 minute. Remember that natural logs are undefined for negative numbers. You cannot have the natural log of a negative number. So many times you will see something that looks like this, a natural log of the absolute value of u. But there is a theorem that tells us that the derivative of the natural log of the absolute value of u is simply equal to u prime over u. So in other words, we can treat this or differentiate it as if the absolute value bars were not there. If I I have the function f of x equals the natural log of the absolute value of the cosine of x. Because the cosine of x can be negative, but a natural log can't, so we have to take the absolute value of the cosine of x. Well, when we take the derivative, we can ignore those absolute value bars and take in the derivative. So the derivative of a cosine is a negative sine over x, negative sine of x over the cosine of x, and that equals a negative tangent of x. All right, so it's fairly easy to find the derivative of the natural log. Hopefully this video was helpful.